So this morning we have the pleasure of hearing from two colleagues, and we're going to start with Lauren Corlies. And let me just say that Dr. Lauren Corlies joined the Education Public Outreach group for Rubin Construction in 2018, and she joined as the Astronomy Outreach Scientist. And not only did she come to the group with her expertise in science and data and education, but she also took on the extra role of being the deputy project manager for EPO. And as that deputy, she also got invited to be the leader in 2021, which she has done, and we've been very grateful for her participation in leading the awesome team and really bringing the closure of the construction part of EPO. And so let me just make sure that I'm saying all the right stuff. And I'll make two more comments. One, that it's not just EPO that Lauren brings to the table, but she actually does have a research focus, which is using cosmology simulations to understand the flow of gas into and out of galaxies. That, unfortunately, is a science endeavor she probably hasn't had a lot of time to pursue, and I hope that my next statement gives her an opportunity to do that, because unfortunately, Lauren has told us that she is moving on to her next endeavor. And what I told her and the rest of the team was that I'm very thrilled for not just Lauren, but also thrilled that the Rubin construction project was able to be the launching point for yet another professional to be able to move along in their career. And so I extend my personal thanks to Lauren for all of her contributions to the construction project, to Rubin Observatory in general, to the entire team. And we wish you the absolute best going forward. And with that, I'm going to invite you.
Good morning, everyone. Thank you for being here, and thank you for that introduction. I'm really excited to have this moment to be able to celebrate what the EPO team has been doing. As Victor just said, we're exiting construction, but we're also entering operations. We're going to get to show off all the things that we've been building that we're going to take with us. But the first question you might be asking yourself is, well, why is education and public outreach part of the observatory at all? And so I'd annoyingly ask you a question in return, which is, how did you come to be in this room? A lot of us decided to be astronomers, and if you didn't, on a different career path, you still decided to come and work for the observatory. So what was it of all of the things that you could possibly do that drew you to want to work for Rubin? My answer to that question, it won't just be rhetorical, I'll give you an answer, was this image when I was in the third grade. It was in my science textbook, and it was the first time I learned about anything in the solar system besides the Earth. And it was that moment of, how can this thing exist? It's so big, is what they're telling me. It's so far away. And I can't say it's a direct path. Like, this was the moment I knew I was going to be an astronomer, but it was definitely one in a series that led me to where I am today. And my guess is maybe it's not this exact image for everyone, but that it's something like this, that it was maybe manned spaceflight was really exciting and that drew you to space, or 30 years of incredible Hubble images at this point that we've all had the pleasure of enjoying. Or maybe you had a telescope, you knew someone who had one, and you just went out and looked up. But there was some moment, some education and public outreach moment that inspired you to want to be to where you are today. And I think it's important that we continue to provide these moments for people moving forward. And beyond just these moments that you take really far, like, yes, I want to be involved in space, you can have an even broader impact than that, as I think we all really personally got to experience last month when these images started coming out from the James Webb Space Telescope. My guess is that everyone here had a similar experience to me, which is people who normally think what I do is cool but don't really ask me about it, were suddenly all texting me. What are these pictures? What am I looking at? Why is this one got weird lines? And having to explain that to everyone was a really exciting moment. And so that's also the power that Rubin can have, to create these moments of wonder and awe for people, and to get them curious and to take them outside of their normal experience and get them looking up. So we're already starting to generate images like this. I saw this one and was blown away. Like, look, it's the building, it's really there, look at the Milky Way. And you need education and public outreach to be able to create these sort of moments. They don't just happen. But in addition to big moments, like things like first light, the end of construction, our team is also really thinking about the everyday. How can every day we bring a little bit of Rubin and a little bit of astronomy to people in a way that they're going to find really exciting? And to be able to do that, you need to put effort, you need to put time, and you need to put resources towards creating those sorts of moments for people. And that's where our team comes in. So since the beginning of construction, education and public outreach has been a full subsystem of the observatory, the same way as telescope and site, camera, and data management. And so we've had the pleasure of having that opportunity to have resources and to build a team to be able to create the really amazing program that I'm going to show to you today. But first I want to start with our mission statement. So EPO aims to provide online data-driven experiences that are accessible and approachable, adding real-world context and opportunities for people to engage with Rubin Observatory and explore the universe. So I really like this mission statement because it tells you both what we're trying to do and also talks about how we're trying to do it. And that's these orange words that I've pulled out. I'm going to talk about a bit so you can sort of understand what was the strategy behind how we decided to build this program. So first and foremost, the program is online. A lot of outreach, I know a lot of outreach I've done, a lot of outreach you all have probably done is typically in person. You're there talking to someone, but then that's limited by the number of people who can talk and who shows up and who you're talking to. Being online gives us the opportunity to have as wide an audience as we possibly can. And more than that, we've really made sure that the majority of the program is designed so that all that you need to access it is a phone. So if you have a phone that can connect to the internet, you can access the Rubin Education and Public Outreach program. Another thing that's been really important to us is to make sure that the program is data-driven. We're trying to highlight not just astronomy, but specifically Rubin Observatory. And one of the really amazing things that we're doing is creating this huge image survey and all of the data products that are going to come from it. So how are we providing the general public with a chance to interact and explore that data? And that's something that's been brought into the different things we've been building. But you can't just take a science tool, a research tool that we all know how to use and place it in front of the public and expect them to have a good experience. Yes, it's exploratory, but it's also a lot of a learning curve. And so what we've been trying to do is to make sure that the things that we're building are accessible and approachable. That when a member of the general public comes to the thing that we've built, they think that it's been built for them, and it encourages them to want to continue to explore and to learn. And we're also making sure to add real-world context. So how does this fit into their experience, and how can they understand it better? And then finally, we want to make sure that we're engaging people. A thing you could fall into with an online program is you just keep swiping through and you look at a bunch of stuff, but you never really interact. So how can we use the fact that it's online to actually build something that people can respond to, engage with, interact with? And so hopefully these guiding principles come through the program that I'm going to introduce to you today. And so the first thing that I want to show off that we've been working really hard on is a new public-facing website for the observatory. So it's not fully public yet, so we're still doing the final touches to the website. But if you go to this temporary URL right now, you can click and interact and see the website that we've built. In fall, when we fully launch the website publicly, we'll take over the rubinobservatory.org URL, but for now, this is where it's living and what you can go and see. The video should play. The trouble with building an interactive program is that you have to screen record a lot of stuff. Okay, great, here it's playing. So here's the new homepage. We're really trying to make it visual forward. Like, let's show people images, let's give them a chance to see things about the observatory. We want to make sure that it's really clean, that it's uncluttered. This is my desktop view. If you scrunch it down, it also looks really good on a phone, which again was important. And another big goal of ours was to make sure we were immediately directing people to the kinds of things they wanted to be finding. So information about the observatory, our education program, new news items, all of that is available from the homepage. Another thing that's a little blurry since the video stopped playing, I can try and play it again. No, it won't play again. There it goes. Is that the website will be available in both English and Spanish. And that's true of everything that we're building, so I'm going to continue to say that throughout the talk. So if you click on that toggle right now, it will toggle into a Spanish version. There's currently no Spanish content, but we have the whole plan in place to be able to do all of the translation this September, so it will be there by the time the website goes public. And then the last thing I want to say is that there's a contact us form at the bottom of this homepage. So as you're scrolling through, you think like, oh, there's a typo. Hopefully there's no typos, but there's probably a typo. You can send that to us. If you have an idea of something fun that you'd like to see on the website, you can also drop that in that form there too. So the About tab I'm not going to spend too much time talking about because it has the sorts of things you'd expect to see in an About tab, the history of the observatory, things about our funding agencies, job opportunities. And instead I'm going to move over to the Explore tab because that one's really one of my favorites. So this is where we've been placing all the engaging but also conversational science content that the team has been creating. That was really a goal of this website, to have the tone be conversational, that when you're here you feel like someone is talking to you and explaining things in a way that you can understand. So it's in this tab that we include things about the technology that makes the observatory possible, the science goals of the observatory, why are we named after JWST Rubin. But I also want to call your attention to a new program that we've been developing called Rubin Voices. So this is building off the great work that the communications team has been doing, making staff profiles. But it takes it a little bit further. The interviews are a little bit more in depth. And we called it Rubin Voices, and what we're really excited about is that it doesn't just feature an interview that you can read with a person. It features actual audio clips of their voices. Because to us, it's really important that we're highlighting who is a part of the Rubin Observatory just as much as we're highlighting what is doing. So you can go and you can hear clips of different parts of your colleagues, saying their name, parts of their interviews in their own words, and really get a better sense of who they are as a person. So this is the content that's there now, but as we move into operations, we'll be able to continue to add content to this part of the website to continue to engage people. Going across the top, there's also another tab called Gallery. So we've created a new gallery of downloadable images, all related to the observatory. So you can go there now. You can see all the images we pulled out. We're trying really hard to pull the ones that we think are going to provide that sort of wow moment. I'll point out that they're all downloadable. So if you are giving a talk about Rubin, this could be a good place to start looking for images that you'll find useful. You can download them in their native form in different resolutions. And again, we provided captions and descriptions of each photo in both English and Spanish. But in addition to just these images, we've also been creating a lot of graphics related to Rubin Observatory. So I've pulled out a few of my favorites, but we're working really hard to build something like a Rubin visual identity, building off the guide that we've already created with all of the graphics that we're also creating. So it makes it really easy when you're looking at something to go, oh, I think that's from Rubin, just based off the way that it looks. You don't even need to use the word. And so all of these graphics will also be available for you, and it makes it really easy to make talks like this because they all look and feel the same, and you can just pull them all together and make a really great product. But we're not just interested in showing static images and static text. We've also been creating an animated video series introducing Rubin, the observatory, and its science goals. Because sometimes maybe people aren't going to want to read 3 paragraphs about Rubin, which is crazy, I know, but maybe they'll watch a 2-minute video about Rubin instead. So this is the moment that was causing different difficulties at the beginning of the day. So for people online, hopefully we can post the link so you can watch it. The video is also available in English and Spanish, and I provided them the Spanish link, so if that's better for you, maybe it's a bonus for being online. And again, this is with English, but also Spanish narration as well, not just Spanish subtitles. So I'm going to play this video now. Hopefully it works and you can see what we've been building.
There are many observatories around the world, so why build another one?
If we bring the presentation
What
back.
makes Rubin Observatory different?
I can only
The
see the screen.
telescope inside the observatory combines technologies in a unique way that opens up a whole new view of the universe. We know that space isn't boring. There's a ton of stuff happening all the time, but many exciting events are actually pretty easy to miss. Sometimes they're really far away or don't give off much light, and sometimes we're just not looking in the right place at the right time. But that all changes with Rubin Observatory. Rubin Observatory's 3 mirrors collect light from a big area of the sky at one time. The telescope can move around the sky really fast, and it has a super sensitive camera, the largest ever built for astronomy. Working together, these features make Rubin Observatory great at detecting faint or faraway objects, and catching temporary events like supernovae explosions or small objects that move across the sky, like asteroids. It's the first observatory designed to do all these things at the same time on this scale. Rubin Observatory is what astronomers call a survey telescope, which means it takes images of the whole sky, not targeting any object in particular. The images Rubin produces are packed with information. They're like treasure chests for astronomers. Imagine all the discoveries we can make now that Rubin is providing our best view yet of the universe in action. Want to know more about Rubin Observatory? Find all our videos and much more on our website and follow us on social media.
It does advance. Is that... Yes. It's all working. Thank you, Aiden. So yeah, but didn't get to... at the bottom of it, what I was also saying is that we've actually created 3 more of these videos that we'll also be releasing in the next year. They're just not quite there yet. But my hope is that that sort of video, like I definitely plan on sending that to my parents the next time they ask me, wait, what do you do again? I can just send them the video and then they can see it. But this is all part of an effort overall of what we're trying to do, which is increasing our social media presence. So again, this is coming back to the idea of we want to reach as large an audience as possible. And if we want to do that, we have to go where people are, where they're going to learn new things and discover new things, and that's on social media. And so making sure that's where we're bringing people content regularly that demonstrates the things that we value, that shows off our team, and that makes it more interactive is a really fun part about social media, is people can respond to you with things that they think are funny, or that you can also provide them with surveys or questions that you can ask them and get responses. So you can really build a sense of community around the observatory by really leveraging social media. And so these are our handles on all of the different platforms, so I encourage you all to follow us at any or all of these platforms that you're interested in. Including the YouTube one there is where the video I just showed is already live. You can go and watch it again if you'd like. So we're going to shift gears a little bit to talk about the interactive data visualizations that we've been building. So remember, one of the things that I said we were really trying to do was make our program data-driven. This is one of the big ways that we're doing it. So the first thing I want to show off is what we're calling Sky Viewer. So the Sky Viewer is our response to the question, how do we bring the whole image survey to the general public? So we've created this tool that is an all-sky visualization that allows people to explore and interact with the image survey, but also the discoveries and the objects that are within it. So this video that I'm going to play is a simulated look at what the Sky Viewer looks like, but I'll say that it's fully built in terms of its functionality, and it's mostly just waiting for better Rubin data to put inside of it. But to show off what it's capable of, so this is the Sky Viewer. It has sort of 2 modes. The Explorer mode is what I think of as the main mode. And so it takes you to this sort of a screen, which will eventually be the Rubin image survey and objects within it that we've pulled out that we think are interesting. Because a big piece of feedback we've gotten about a tool like this is that people kind of don't know what to do if you just provide them an empty sky. So we're giving them starting points of how to interact with the tool. So they can click on things, identify things that are interesting. We're building in search and filtering capabilities that are more in line with the types of questions that people are going to be asking. I want to see all of the galaxies instead of like, I know the exact RA and DEC of the object that I'm interested in. So they can click on individual objects and it'll give them information about them, both numerical and also narrative. You can pan and zoom throughout the image survey and really get a sense of the scale of what we're trying to do. It'd be a shame just to give people individual static pictures when there's all of this context that they're missing. But for those people where even that guided experience is maybe a little bit too much, we've gone even further and created tours for them. So this is within the same tool as the Explorer mode, which I like a lot. So the idea is that you're a little bit nervous, you maybe don't know what to do. You take one of these guided tours, it introduces you to different objects, but it also drops you in the same exact view as the Explorer mode. And so hopefully you do a few of these tours and then you gain some confidence and you can go into the Explorer mode and start asking your own questions about the data. And right now, I'll add that we're working to ingest data, preview 0.2 data into it, so we can really get a sense of what is the Rubin data, what does it look like, how can we make sure we're transferring Rubin data into the Sky Viewer when we move into operations. What the Sky Viewer can't do is really show off the amazing solar system discoveries that we're going to be making. And so to do that, we've built another interactive data visualization that we're calling the Orbit Viewer. So hopefully you're getting a sense of we're building things that look and feel the same way, that these are Rubin tools that we are presenting to the public. So this is an interactive 3D visualization of the solar system that has a lot of things in common with the Sky Viewer, but is also different. So again, there's an Explorer mode. There's this sense of different objects that you can click on that we think people will be interested in to guide them through this experience. Fast forward a little bit. And then it takes you into a tool where it's going to be a 3D visualization of the solar system. We're working really hard to make sure that this is displaying essentially accurate orbital positions. We're also hoping to visualize upwards of around 30,000 objects. So So this is still under active development, so that number will probably change as we continue to build it, but that's definitely the goal that we're aiming for. Again, showing the different search functionalities and filtering capabilities. It's also going to provide you the ability to click on individual objects in the solar system and to be able to control the time and speed of essentially the simulation that is playing, so people can see things moving faster or slower or at different dates that they might be interested in. And I also want to say thank you to the Solar System Science Collaboration, who's been helping us get databases and data that we can put into this prototype as we're building it. So those are really exciting. We really can't wait to be able to show off and have people interact with the data that the observatory will be producing. But as we all know, most of this data isn't available yet. And so we're moving into operations thinking, okay, well, what can we do while we're waiting for the rest of the observatory to finish? How can we provide interactive content to people, or an experience where they're still clicking, interacting, learning about Rubin, but it's maybe not data-driven? And the answer that our team came back up with in January was, well, we'll build a bunch of games for people. Everyone wants to play games. And so I'm really excited today to get to introduce a game that we're calling Rubin's Space Surveyors. So this link here, spacesurveyors.app, is also active. You can go to that right now. If anything, I might be the first person to ever give a plenary and say, please take out your phone and type this URL in and play this game as I'm talking about it. That would make me really happy. But what I'm also going to do is I played the game a few days ago and I recorded myself so I can talk about it right now. So the idea behind this is that one of the things we find really cool about the observatory is the scheduler. How is it going to decide where it's going to look and what it's looking at? And so this isn't exactly that, but it gets people towards that question, how do you choose what you're going to look at? It also introduces them to the idea of a transient sky, that things are coming and going and that we're trying to find as many of them as we can. And so you get to make decisions of what types of things do I want to look for? Where do I want the telescope to point? You also get a sense of slewing takes time. So if you're going to look for one thing at one side of the sky and one on the other, you're going to pay the penalty to move the field of view all the way over to that part of the sky. There's also moving objects, and so you have to make that decision of like, where should I put it so that the object moves into my frame when my image is going to brighten, when my cursor is going to be there to take the image. We've also pessimistically added clouds to remind people that sometimes you can't always observe the things that you want to observe. So if a cloud comes over your field of view while it's capturing, it's not going to count any of the things that are behind the cloud. And then the sun comes up. I know, I got so close on that one. I really wanted to catch it. This was a really big team effort. Alexandra teased this at her talk on Tuesday. She said that she built this whole thing on the front end, and it was a whole team effort to design it and come up with all the content that was going to be inside it. And so that last screen had, congratulations, I discovered 14 things. It's actually not that great. You all can definitely beat my score. We also added a share score button. So if you click on that, it'll generate something onto your clipboard that you can then share, so either in a Slack channel or on your social media platform of choice. But our hope is that people get excited, and I definitely want to play this over and over again, because I can definitely do better than 14, which is also a big point of making a game. Okay, so I'm going to switch gears a little bit because we've been building a lot of things for the general public, but we've also been thinking a lot about education. And it's really been, I think, one of the biggest things that we've been working on for a while, and something that I'm really quite proud of is our formal education program. So when you're thinking about building something specifically for classrooms, there's different things that you need to be considering than if you're building something for the general public. So for us, our big three priorities were, we want to make sure that the things we're building are engaging for the students. And we're really aiming to bring authentic astronomy data into their classrooms, and so they can get that feeling of they're working with data in some ways like the ways astronomers would actually work with data. We want the things that we're building to be teacher-friendly, so we want them to be designed and tested by teachers. We want them to be useful in their classrooms, so we've been thinking specifically about the curricula that teachers in the US and Chile are required to teach to, and making sure all of our materials support teachers in teaching that curriculum. We also really wanted to make sure that it was a low-stress technology. Classroom activities exist using astronomical data, but a lot of the time they require you to download software, or they require you to download data files, which makes sense until you think about a teacher who maybe has to deal with a firewall, or there's multiple computer labs and they put all the work prepping in one, and then randomly on the day they're supposed to use it, they get assigned to another. So how could we do something that would remove that stress for teachers? So the program that we built focuses on advanced middle school students, high school, and introductory college students. So some of you might teach some of those types of students. This program could also be useful for you. It's designed with a progression of concepts and tasks, all estimating to take about 1 to 2 hours in the classroom. And we've user tested all of these materials with real teachers and students. So over 5,000 teachers and students have looked at this program that we've built. We've been able to incorporate all of their feedback. So what we've generated is a browser-based program. So you don't need to download anything, just like the rest of EPO, you go to a website and the program works. And it's designed such that any teacher can feel empowered to bring this into their classroom. They don't need an astronomer, they don't even really need a really strong astronomy background to be able to use these materials. So this is also hosted on that website that I started the presentation with in the Education tab. You can see there's 3 big components here. You can learn more about the full design of the program and the program guide. There's the investigations, the actual classroom activities we've been building, and all of their support materials. And then ways to get involved with professional development, how we can train you and help you use these tools in your classroom. If you click on investigations, you see these icons. So we've built 6 of these classroom investigations. One, we've fully incorporated all of the feedback we've gotten into, so that's surveying the solar system, and that one is launching this fall. And these other 5 will follow shortly thereafter as we continue to update with the feedback that we've received. So if you click on surveying the solar system, you see this screen. So as I mentioned, we tell people right up front, we expect it to take 2 hours in their classroom. And we provide them with all of these support materials, a teacher guide, the investigation itself, how they can implement it in their classrooms, assessments they can use to see if the students reach the outcomes that were desired, phenomenon, and also auxiliary materials, so other things they can use in their program. The teacher guide itself is yet more information that we really think will support people in using this in their classrooms. So an introduction to the concept, what things do teachers need to have taught before we think students will be able to come to the learning outcomes that we hope that they will with this investigation. We've also specifically identified the standards in their curriculum that this applies to. So it makes it really easy for them to feel confident that this is something that will be useful for them. I also really like we thought about common student ideas or misconceptions or questions that they might ask you. That was definitely something when I used to teach, you get a little bit nervous, you never know what curveball they're going to throw at you. And so we can take at least a little bit of that stress out of it too. So I encourage you, this is up now. You can go and click start the investigation and go through the whole thing yourself if you want. As an astronomer, it'll probably take you closer to 30 minutes as opposed to 2 hours. And it's really actually a lot of fun. But what I'm going to do is call out a few of the highlights of what is in this program with just one short video. So remember, this was meant to bring real data into astronomy classrooms. So this is real astronomical data that I curated when I first joined the team. So what you'll see is the interactivity that we're really excited about. So this histogram, you can hover over it and it gives you information about the specific bin. You can move between different types of objects in the solar system just natively in the browser and compare amongst them. And you answer the correct questions exactly in the screen that you're looking at. We give students a sense of the progress that they're making, and we also congratulate them for making progress, because that was some of the feedback we had got, is sometimes it can feel long, and you need those moments to sit and just feel proud. This is another interactive moment that we put in the investigation where you can see sort of the solar system in context, all labeled with the sun and other planets, so people have reference points within it. Another piece of feedback we got was a reset button. You can really get discombobulated when you're moving around, and so taking people back to where they started, and also allowing them to control the time step of how these objects are moving so that they can really successfully answer the questions. So all of this interactivity, like I said, just works directly in the browser. And 2 more of these investigations at least are coming this year, so there'll be a total of 3 by the end of next year. So I'll just citizen science projects, and then we can have as many Rubin citizen science projects as there are people interested in making them. So right now we've been really focusing on the infrastructure. How can we build infrastructure that makes it really easy for you to go in and curate your data on the Rubin Science platform and then move it directly over into the Zooniverse project builder, because the Zooniverse will host all of the Rubin citizen science projects. So that infrastructure is mostly in place to be able to take data from one and move it to the other directly. You no longer need to download data and then re-upload it. The scale of Rubin is way too big for that. So then when you get to the Zooniverse, you're presented with a tool just like this. It helps you build the web page. It tells you what sort of content you need to provide to create a successful citizen science project, and then you're good to go. So our team is working closely with the Rubin community engagement team, as well as the Zooniverse, to coordinate supporting these projects, any development services you might need to make them successful, as well as marketing. How can we help you get people to actually come and participate in your citizen science project? So that's the end of what I was going to say about the program. That is the program that we have built. But I also wanted to take a moment to acknowledge the team. I didn't do this alone. I also want to apologize to my newest team members because I forgot to take a picture of us at our team retreat 2 weeks ago. And so you're not featured on this slide, and I'm very sorry. But we are a small but mighty team who built all of this. So we were never a team that was bigger than 9 people at any given time to build this whole program. And we were able to do that by really leveraging all of the experiences and expertise that our team members are bringing. So we're a team of scientists, but also educators, graphic designers, writers, web developers who have made this program possible. And in addition to what we've produced, I'm also really proud of how we worked together to produce it. We all worked really hard to be a team that was a team culture of respect, of open communication, and that was really important for delivering something as ambitious as this program. So I wanted to take a moment to say thank you to my team, because this work was really more fun than anything, and that took work to make that true. So finally, I want to say this is a retrospective. This is what we built in construction, but we're also looking into the future. We are moving into operations. And I've been calling out how we can continue to add content to the website. We'll make more videos. We'll expand the education program. And that's all what we're going to do in the future. But I think it's also important to ask, why are we doing any of this? We have this moment where you can reflect. What is the impact that we're trying to have as we're building this observatory? And for education and public outreach, another way of asking that question is, what does success look like for us? And I think for us, our hope is that these tools resonate with people, that someone stops and has an authentic, exciting experience with Rubin and with Rubin data, and that these tools are also useful for other people who want to do outreach about the observatory. Because ultimately, our biggest hope is really that together we can show the world just how amazing the Rubin Observatory is. Thank you. We have some time for questions, but yeah, okay, great. I'm getting the thumbs up. Okay, I think I saw you walk up first.
Yes. So can you say a little bit about sort of press releases and how Rubin will appear in the press? We've all been very impressed by how JWST has done and sort of built that excitement in the New York Times and many other places. What will Rubin be doing along those lines? And is indeed that part of EPO?
Yeah, so I didn't call it out, but we are in fact definitely planning press releases for things like the different First Light events that are coming up. And our goal is to make just as big of a splash as people did with JWST. So making sure that we have all the multimedia assets that we're preparing. So yeah, all of that work is definitely continuing for sure.
Good. First of all, amazing. This is best looking website ever. I love it. It's all great and gorgeous.
Thank you.
My question is, astronomy is obviously a very visually driven science,
Yeah.
and that causes accessibility issues. And
Yeah.
of course, it makes very much sense that we will focus on a visually driven website.
Yeah.
But can you speak a bit about accessibility, both for the blind and visually impaired community and other communities that you have implemented on your website and framework?
Yeah, thank you. Yeah, we're definitely trying to always remain cognizant of the fact that just providing visual materials isn't going to be successful. So one thing that we've done for the website as built is that it's fully compatible with screen readers. So you don't need to be able to see, you don't really even need to be able to use a mouse and keyboard to fully interact with the website. And that was really important to us. We're also building communities of practice. And so making sure that we're online, we've created a Facebook group for teachers, and where a lot of people are interacting and trying to find that sort of content. So we'll be there for them, as well as email listservs. And so we're doing a mix of everything, going places and also trying these online efforts as well to make sure people know about the program.
Lauren, everything you've generated is fantastic.
Thanks.
I noticed that you've really helped with the accessibility and making it browser-based, so there's no software, there's no download. I am acutely aware recently that the US is in a privileged position when it comes to bandwidth. And the same is not true worldwide, and it can be quite patchy or intermittent. Is there any scope for developing these apps in a way that could be applied standalone or post-download?
So not requiring the internet?
Yeah, for those communities where internet is not necessarily that reliable.
Yeah, I think we've definitely focused on trying to make it online. And so I think pivoting away from that, not impossible, but it would take some resources away from building new things. That would be part of the judgment call. I'd say most of what we built, I don't think requires too much bandwidth, with the exception of the interactive data visualizations. Those require a lot of effort just because of the number of things that we're visualizing. But the education program in particular, I think that would be especially important thing to consider. The amount of data a student is interacting with at any given time isn't that high. And so our hope is that even in maybe not the best of internet situations, it could still work. But yeah, it's a limitation of going online for sure. Okay, I'm being pulled off the stage because we're out of time, but I'm around all day. So if you have questions, you can definitely come and find me. Thank you, everyone.
Thanks. Please do post your extra questions in the Slack where the EPO team is going to answer them. Okay, so next up we have our science keynote speaker, who is Marcia Rieke, who is here with us today. She's a Regents Professor here at the University of Arizona. Marcia started her career with undergraduate and graduate degrees in physics at MIT. Her research interests focus on galactic nuclei, near and far, and building large format, low noise infrared detector arrays. Marcia is currently the PI for the near infrared camera for JWST, which, as you know, just underwent commissioning and first light. So Professor Rieke is here today to talk to us about JWST and Rubin Observatory, engineering, commissioning, and science. So please join me in welcoming Marcia to the stage. So we might go a little over time today. We might push a little bit into your break. Hope that's okay.
Okay, it's a pleasure to be here and to see some old friends that I haven't seen in quite a while because I've been holed up in Baltimore for reasons that you might guess. So I want to give you a little bit of a flavor of what it's like to commission a complicated observatory, and also give you a little bit of a sense of not just the science that Webb does, but rather some of the aspects of Webb that might interact well with things that people want to do with Rubin. I mean, they're very different kinds of telescopes. Webb is the ultimate point at one spot and stay there for a long time and go very deep, as opposed to surveying a big area. But there are some commonalities in some projects I think that would benefit each other. Okay, let's see. Can we get the slides to change? Maybe. There we go. So I had a nice Christmas morning. I watched the launch, and then I opened up a present from my sister, which were these cool earrings. And of course, once the launch happened, that was first sigh of release. That was sigh of relief number one. And then as the subsequent 10 days proceeded with the telescope unfolding, the sun shield unfolding, with each step, another sigh of relief, because there were many naysayers that said this was too complicated and it would never work. And it was much easier to deploy the telescope in space than it was on the ground. On the ground, the sun shield was just a nightmare. It took so much gravity offloading and this and that. It took a couple months to manipulate the sun shield. And on orbit, it was a couple of days. So remarkable. And of course, we're way out at L2. So we're 1.5 million kilometers from the Earth. No chance of servicing. So we had to get it right the first time, and that's why we did huge numbers of tests and rehearsals and so on. Now, I think most of you probably have an idea of what JWST looks like, and we have a warm side on the underneath, so to speak, where all of the sort of support things are, the antenna that sends things back to the ground, and the support computer and so on. And there's the cold side, and the cold side, of course, is where the action is. And the instruments are, I'll show you the optical layout in a little bit, are bolted on the back side. So it's like a Cassegrain, but it's not a Cassegrain telescope. The focal plane is shared so that we can run 2 instruments at the same time. In principle, one could even run 3, but the data rate back to the ground right now would not really work very well. And one of the things that's been remarkable through this early part of the mission is we've got a timeout here.
For people who don't know, none of our virtual participants can see the slides. So we're going to have...
One of the remarkable things about the launch was that Arianespace absolutely nailed the launch. The injection was perfect, and we had to use relatively little fuel for the 2 mid-course corrections that were required to get the telescope to L2. As you might guess, the initial launch was done in a way where you wouldn't quite get to L2 because if we overshot and had to turn around, that wasn't going to work very well. So the 2 mid-course corrections were to get it to the point where the telescope would end up at L2. And they were done so well that we now have enough fuel left for station keeping that the mission might last for 25 years. I can tell you that the filter wheels in NIRCam were tested to that kind of a lifetime, but on the premise that we were proving that it would last for sure for 5 years. So we'll see how that all goes. So you might think that JWST and Rubin as missions don't have much hardware types in common, but we actually have some similar challenges. JWST is not a standard Cassegrain telescope. It's a 3-mirror anastigmat with a fine steering mirror that's used to stabilize the pointing. And of course, it has 18 mirror segments that have to be aligned initially and have to be kept aligned. And so there's quite a bit of technology that goes into all of that. And you know, I used to think that my camera's 40 megapixels sounded pretty cool. Well, you guys forget it. 40 megapixels is nothing, but I will say that 40 megapixels for an infrared camera at 40 Kelvin, 1.5 million kilometers away is still somewhat of a big deal. And so, you know, I'm not totally ashamed of only 40 megapixels for NIRCam. And so far, so good with the detectors. They have been working superbly, and we have not had any real issues with them. There have been a few quirks. We discovered something that we call space balls, which there's some cosmic rays that when they hit one of these Mercad telluride arrays, the charged particle hits a heavy nucleus in this material that, you know, isn't just relatively light nuclei like silicon, and we get a much bigger effect, and we actually have seen sort of some little sparkles off to the side that we call shards, and so we've had to learn to deal with that. But those kind of hits aren't as numerous as the usual cosmic ray hits that we have to deal with. So the fact that you have lots of detectors. We don't have quite so many, but we have to send them all back to all the pixel data back to the ground, and that has proven to be challenging sometimes. And although NIRCam could be read out and you could save every read of every pixel, all 10 arrays, 10 times every 10 seconds, we can't send that to the ground. So we had to devise some co-adding schemes and so on. So the commissioning process, this was, of course, what's occupied me since January. NIRCam was the first instrument to be completely turned on, and we actually started operating at 100 Kelvin, even though the final operating temperature is 40. And that's because our short wavelength detectors are sensitive at that warm a temperature. And so we could start rounding up the 18 images from the different mirror segments. And so starting somewhat warmer meant that we saved a few days of commissioning time. And so the whole commissioning process for us was going from this picture you see in the upper left with, if you count them, there's 18 spots. And we got that into a beautiful diffraction limited image. And the image is diffraction limited at a micron, even though the requirement was 2 microns. So the alignment, the telescope has worked superbly. And of course, once we had the telescope lined up, we had to bring all the other instruments online, and we had to finish commissioning NIRCam and getting everything ready for the General Observer program. And there was also a program of early release observations, EROs, and that's all the pictures that you've seen. And there's another program called ERS, Early Release Science, where teams competed for roughly 100 hours each of time very early in the mission. And their role is to explore the different instrument modes and get data out to the community as quickly as possible, along with some tools, tips, hints on how to analyze the data. So I don't expect people to look through, I've got several of these kind of timeline plots, but I wanted to give you a sense of the detail of planning that went into this commissioning. So this is the very top level commissioning timeline. And so the very first part in orange was the spacecraft commissioning, where we did these mid-course corrections. That's what the MCCs are. And we had to start doing a few things, particularly for the mid-infrared instrument, which has a cryocooler. And there were various tests of the attitude control system and so on. And then NIRCam got turned on, and this black box labeled transition is when we started collecting these first star images. And OTE is JWSTEs for optical telescope element. Don't know why we can't just be a telescope, but anyhow, that's what OTE is. And that green bar then got the telescope fully lined up as well as we could, which proved to be very well. And then we went into testing and commissioning all of the instruments. The telescope alignment part alone had an enormous number of steps, all of which had been don't have exactly the same optics, don't actually have a star at infinity. And when we had our last cryogenic test at Johnson Space Flight Center, we went through as much of this as we could without having a flat mirror that would go all the way across the mouth of the telescope. So we had to do this in some steps. And you'll notice this thing called SIF, Science Instrument Aperture File. That got updated a number of times as we homed in on exactly where each instrument was located. So we had all the pixels located relative to all the other pixels. We got the cryocooler working, so the mid-infrared instrument would come on board. We checked that that cryocooler didn't induce any jitter. It didn't. We couldn't tell that when it was turned on. The pointing was just as good with it on as it was off. And then there's 2 long bars that are labeled MIMF, multi-instrument, multi-field, because if you go through all of the thought process of how you line up this telescope, there were some ambiguities between tilt of the secondary, the location of the secondary, and tilt of the primary mirror, which are best resolved by looking at how things change over the full field. And so the first one of those was done completely. And it turns out at the end of that, the alignment was so good that we didn't do any changes for the second one. And this slide just gives you a quick overview of all the steps. And of course, I suspect that for LSST, you've got a similar kind of very stepped approach where you check out the alignment of each part and get everything tuned up. And of course, with this 18 segments primary mirror, we have to do extra things to make certain that those segments are all lined up. And that's what the little sort of purple magenta things are in the lower left. There's a part we call the dispersed Hartmann sensor that has prisms that go across each pair of mirror segments, and you look at how the light between those segments interferes, and that gives you a measure of how far out of focus they are from each other. And with a total of 20 of these, you can completely resolve the phase of all 18 segments. And that went very well. And those images are all taken with NIRCam again. Ooh, let's change it. Okay, I guess it's still projecting very well. And so this last step here, the fine phasing, is done every couple of weeks or as needed, and we take the data to look at that during routine operations every couple of days. Now let me see if I can get back to where I can change. Okay. The screen changed appearance and okay. So this wavefront maintenance, I'll comment that the project is making available the data from those, and so people can find optical path difference maps for times close to when their own observations were taken, and they can then recreate PSFs that match their particular date. So the first step in getting the telescope aligned was just finding the segments, and NIRCam was going to be used to cover an area almost as much sky as the full moon covers. And as it turns out, what ended up being the case was we found all the segments, but let's see if I go back. You can see in a relatively small fraction of the area that was to be surveyed. And that was our first clue that everything was trending in the direction of going better than we had hoped. And there's all 18. And it's a little bit hard to tell much about them. But then they get put into a specific layout. This was part of what had been thought through long before we got on orbit, and there's a numbering plan and a clear-cut path. If you see this in this image, what do you do? And if you look carefully, you can see that number 7 and number 11 are very much out of focus. Those are the bottoms of the deployable wing parts, and so that's not too surprising. And a number of these have, in particular, quite a bit of astigmatism, which is because their tilt isn't quite right. But there was nothing when we saw this image that gave us pause. Everything was displaying a kind of aberration that we knew how to fix with the controls for each mirror segment. And so that was done, and that is the result. This image was when everyone this is when we had the party, the champagne, blah, 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 blah. And this particular image is diffraction limited at a micron, and the telescope is still, even in spite of a few things I'll tell you about with micrometeoroids and like, still doing that. And if you look hard at this image, you can see some galaxy shapes in the background. And in fact, if you just take a look at this alignment image at 3.5 microns, you find zillions of galaxies in the background. And that's now become a recurring theme with JWST, that we are so sensitive in the infrared that we see lots of galaxies everywhere. And I say, you know, we have these galaxies photobombing all of our pictures, and you know that it's a real photobomb when people put a piece of chorizo on the web and claim it's on the WEB web and claim that it's a JWST picture, and someone on social media says, oh no, that can't be real because there aren't any galaxies in the background. So here's a quantification of that optical performance, and we're discovering that this is just opening up some things that we hadn't thought about. One of the early release images has a galaxy, the foreground galaxy in Stephan's quintet is 12 megaparsecs away, and it's resolved into stars. And that was not, to be able to do that was not predicted ahead of time because we didn't know that the image quality could be this good. The bad news was we got hit with a micrometeoroid. We had some little hits all along that didn't do anything particular. There was one that you can just see the damage peeking out from behind one of the secondary mirror struts. And to quantify this, it changed the wavefront error from 50 nanometers to 60. And the telescope plus NIRCam was supposed to be 150 nanometers. And so if we had just met the original requirement, we probably wouldn't have noticed the image degradation. And we're hoping we don't see any more like this, that it was a piece of bad luck. The small hits are occurring at the rate that was kind of predicted by the people at Marshall that track natural space debris, but only time will tell. We got on to NIRCam commissioning and commissioning the other instruments, and we had a whole sort of thought out way we were going to go through in making certain that all of the different modes and all the different functionalities played. This is something that you guys will have in a different sense because you don't have a spectrograph with multi-slits and all kinds of things that require target acquisition and some extra work. And the one thing that was tricky for NIRCam was we started operations at 100 Kelvin and kept working on being the wavefront sensor until we, well, for all time, but well before we got down to the operating temperature of 40 Kelvin. And every instrument had a flow chart of how these different steps went one to the next, and these were very useful, and that allowed us when one instrument team was having a little bit of trouble, the NIRSpec team had a couple of hiccups with their multi-slit actuator device, and we could then trade off and reorder the activities so that we kept going all along and wasted as little time as possible. And so having well thought out and rehearsed commissioning plans was one of our secrets to success. And another part of commissioning that any new telescope has to face is that, the instrument folks could say, if I could just do a little more, tweak this and that, we could do better. You have to decide, when do you finish commissioning and start blending in regular operations? And with the 17 different modes of instruments on the web, there was a lot of potential for, dragging our feet and having a good time tweaking the instrument. Well before launch, we had set up the criteria so that we knew that, maybe we weren't fully calibrated, but we knew that we were operating well enough that we could then turn things over and start doing operations. And the last few weeks of commissioning, the early release observations and the first guest observer observations were blended in as we finished off some of the commissioning modes. Here is one example of some fun commissioning data that also highlights another thing that happens with the segmented mirror telescope. We'd set up a criteria for what a transit observation, what the noise would have to be. Turns out we had no problem meeting that. In fact, it's been quite amazing how easy it has been to get the first order results of transit spectroscopy out, and that was one of the early release observations from the Canadian NIRS team. But we noticed something very funny in our transit observation. There was a jump at the bottom of the eclipse, and the question was, what is that? Well, what it was the following. The way NIRCam works in transit mode is that the short wavelength, NIRCam has two arms. We can take data short wavelength, 0.7 to 2.3 microns, at the same time that we take long wavelength data going anywhere from 2.5 to 5 microns. And in our long wavelength arm, we also have some grisms, and that's what's used for the transits. And so in the short wavelength arm, we put in one of the weak lenses that defocuses the telescope and is generally used for wavefront sensing. But that is a way to monitor what's happening to the telescope while we're taking the transit spectrum, which helps give you another handle on things that can degrade the noise. Well, that little jump in the bottom of the eclipse, if you look at the bottom row here, you see first one of these weak lens images. You can kind of make out the 18 mirror segments. And the subsequent images are later ones subtracted from the first one. Everything looks fine. But then near the end, you see that one of these segments tilted, spontaneously tilted. And that's what caused the jump in the light curve. And these tilt events we still are seeing occasionally. We think the rate is going down, and we think it's a form of stress release from the original cool down. And of course, time will tell. Hopefully they all go away. But at least for NIRCam, we have a built-in monitor if that happens during a transit observation. And of course, I think everyone has seen many of these early release observations. And, you know, the one thing I found quite amazing is that the one in the lower left, the deep sky one that President Biden introduced to the world, has already generated over 20 papers. And so it's pretty clear that the high redshift community has been hungering for something beyond Hubble for quite some time. The bottom right shows the transit spectrum reduced very quickly, doesn't have all the fancy bells and whistles that one can apply, but it detected steam in this exoplanet, and this was done with the Canadian instrument. And the picture of Stefan's quintet that's on this slide highlights the mid-infrared MIRI's capabilities, because if I showed you just the NIRCam image of that, if you look at the cartwheel image, there's a galaxy, the one galaxy in that image that looks sort of bluish and very smooth. Most of the rest of Stefan's quintet looks rather smooth like that too, in the near infrared where you're seeing the stars. But MIRI reveals of course, the dust in the interstellar medium and makes for visually appealing pictures. And here's another example of a photobomb right in one of the early release observations of the Southern Ring Nebula. And at first I thought this was some kind of, what was this scratch on the picture? It's an edge-on spiral that just happens to show up when you observe this nebula with the infrared capabilities that you have on Webb. So you have to get used to seeing a new class of vermin on the sky galaxies. So let's think a little bit about how you might use JWST and Rubin together. And because JWST's greatest strength in many regards is the infrared spectroscopy that it provides, that we've never had in space before, and which is far more sensitive than anything you can do on the ground because there's no OH air glow or other sources of background. So when it comes to following up Rubin discoveries, there are many cases where I think you will find this kind of spectroscopy to be interesting. And of course, not to leave out NIRCam, NIRCam's ability to provide you with high resolution images and spectral energy distributions out through 5 microns, and then you can pick up with MIRI, I think will give you new tools for figuring out the unusual things that we know that you're going to be discovering. So as an example of the spectroscopy, one of the early release observations included some of the multi-object spectra from NIRSpec. And so this slide shows you which objects were observed, and you can't possibly read the little numbers, but The one on the bottom is a galaxy 13.1 billion years look back time. The top one is only 11.3 billion years look back time. Poor thing, not so far away. But when you actually look at the spectra as now used for, I think there's now 7 or 8 papers in the archive analyzing these spectra, and it's just amazing what one can see. There's a 4363 angstrom auroral line of oxygen that has hardly ever been seen, and certainly not seen at redshift 8.8 before. And that just opens up all kinds of new things that you can figure out. And this is just scratching the surface, because these early release observations were fast. They didn't take, these are not hugely long exposures. And JWST also has some very interesting capabilities for just following up and studying solar system objects. And one of the things that was realized when I was back on what we called the interim science working group before there was a real project was that JWST needed to be able to track moving targets. And it was a good thing that we got started with that idea early on, because that meant that it actually got implemented in time, and the Planetary Sciences Division at NASA headquarters chipped in to help make some of that happen. And it's also, there's a lot you can do with relatively low resolution spectroscopy. You can do a lot of diagnostics of what kind of ices and so on are on the surfaces of some of these objects. In the mid-infrared, you can measure the thermal emission from these objects, a lot of outer solar system objects, which gives you yet another handle on their characteristics. And here's, oops, this didn't. All right, well, part of my slide got covered up that showed how far we had gotten in terms of actually testing moving target tracking during commissioning. We tested on targets moving anywhere from 3 milliarc seconds per second up to about 67 milliarc seconds per second. And you can see from this cumulative plot that even near Earth asteroids are within reach, so that if you have a moving target that you want to observe, JWST is ready to do that. So this is one of the things I was mentioning about this NGC 7320. You can see in this image that it is resolved into stars. And this was not, as I say, it was not expected at this distance, but it's because the image quality is so much better than we had predicted. And there had been work in the past, some people were concerned that, well, the infrared filters are so different and that the color magnitude diagrams are going to be blah, 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 different and so on. Well, it turns out when you actually look at the NIRChem filter set, they can be very useful for studying stellar populations. And one of the early release science programs is doing exactly that. And I know of other groups that are analyzing the 7320 image because it's available now, and you can see what you can do with your software to figure out what's going on in that galaxy. Exoplanets are going to be a big topic with JWST because it's proving to be a good platform for doing transit work. And all 4 instruments have different ways of measuring transits. The Canadian nearest instrument has something they call SOS, Single Object Slitless Spectrometer, which uses a curved optic to spread the light out. You can see that the kind of red line in that top spectrum is actually the light of a single star that's been spread out so that they can look at brighter things and that it gets rid of some of the systematic effects. And all of these have been checked out in commissioning, and there's now there's also an early release program that involved a large fraction of the transit community, and I think some results, they've taken some data with that program, and I think they'll be having some results maybe in a press release in a few weeks. And I should mention that the near to mid-infrared are great places to do transit spectroscopy because for an exoplanet, there are a wealth of molecules that have all kinds of absorptions in the 1 to 28 micron range. And one of my great hopes is that before we're done with JWST, we'll find another planet with an atmosphere whose composition is similar to that of Earth's. We'll see. That takes a little luck and some persistence. So let's talk about another way that Webb and Rubin could work together. It is not Webb's, JWST's strength to slew fast to a target and get on it. But on the other hand, it's not completely impossible to do that either. The first little hiccup is that because of the sun shield and having a restricted range of pointing so that you don't get any sunlight on the telescope itself, there's only about 40% of the sky that can be viewed at any one time. So if you have a rapid response transient object, it's got to lie in that 40%. And of course, to trigger an observation, you have to upload the commands during one of the 2 4-hour-a-day connections we have to the Deep Space Network. And of course, preparing the command upload itself might take a couple of hours depending on how complicated the observation is going to be. So you can kind of see that getting onto a target much faster than a day is it's not totally impossible, but not probable. On the other hand, JWST does have a target of opportunity program. And so if you're lucky enough to have something interesting go off in the 40% of the sky that can be accessed, then a target of opportunity observation, whatever you want to do, if it's getting an infrared spectrum, whatever, can be triggered. And there are 3 different categories, proposal categories for these triggerings. One is for what's called a non-disruptive target of opportunity. And this is a case where you discover something that you couldn't know where it was going to be ahead of time, but you don't have to get on to immediately. 14 days is kind of the time scale for those. A disruptive TOO would be one where you get on quicker than that, and an ultra-disruptive one is one where you would get onto the target in less than 3 days. And so a proposal would describe what the kind of source is, what's the need for JWST data. I'm guessing it'll mostly be infrared spectra, but I could be wrong, and what the trigger criteria would be. And so this is, I think, this has not been terribly well advertised, but it's available. And just a kind of, a teaser of what you might want to do. This is a near-infrared spectrum from a kilonova 4.5 days after, it went off. This is the initial gravity wave source. And so 4.5 days is plenty of time for one of these ultra disruptive kind of things, or even the medium disruptive. And the infrared spectra can be quite diagnostic of looking for the specific fingerprint of the elements that should get produced in this kind of event. And I note that, people think about targeting with near spec, that it has all those multi-slits and you have to have accurate astrometry and blah, blah, blah. Well, it turns out that near spec for a single target has a 1.6 arc second by 1.6 arc second slit. And with the use of Gaia stars, we've discovered that the absolute pointing of the telescope is excellent. We typically get within 1/10 of an arc second. And so if you have reasonably decent coordinates for your transit target, you could hit this particular square slit and be in business and not have to worry about all of the grief of the near spec multi-slit part. But this large aperture is part of near spec. You can use the high resolution R2700 grading if that's what's attractive, or you can use the low resolution prism, whatever. And just to give you a sense of the power of JWST, these are light curves of the gravity wave event. The spectra that I showed you earlier with the auroral oxygen and so on, those detections, those were objects at AB 26.5. You'll notice that 26.5 is kind of at the bottom of this, these light curves. And so things, if there is this kind of gravity wave kilonova event that Rubin discovers in tandem with the gravity wave detector, boy, you could go to town and get really high quality infrared spectra quite quickly, and it wouldn't be hard to follow over time. So let me conclude by just saying that now that we have this projected lifetime of 20 plus years, I think JWST can play a role in following up Rubin discoveries. And there may be things where people will discover something with Webb and want to go back and look at the time history with Rubin. We can play together nicely. And the next, there's a cycle 2 call for proposals later this year, but I think that's premature. But you might want to start thinking about things for the cycle 3 proposal call in October 2023. And I urge us all to use our telescope resources together, because I think we're going to learn more by combining data sets than pretending we're just separate missions. Thank you.
You have time for questions, so go ahead and line up at the microphone.
Thank you for showing us all of this. This is really spectacular, and we've seen a lot of these images months ago, but like every time we see them, it's just amazing what this machine can do. And thank you for spending decades actually building it. So my question is about the vermin.
Which are my favorite topic.
I don't know how data analysis is done for JWST. Is every single image that's taken being analyzed through a pipeline and then these galaxies cataloged and placed somewhere, or is that being left over to the PI? Where I'm going with this is, given they're everywhere, it would be wonderful to systematically basically catalog everything that shows up.
So there are some deep survey programs where the teams will catalog and the Institute pipeline prepares mosaics, and they do have some kind of photometric catalog preparation, but right now I think that's relatively primitive. And at the moment, there is not a program to go through the people that have proposed to do these survey observations have plans in place to release catalogs, and we'll all get to see what's going on. But these ones that are being found serendipitously, there's nothing being done right now. But that suggests that the longest proprietary period for any of these data is a year. And when that expires, one could imagine that you could have quite a creative archive proposal to go through and generate a much larger database of interesting galaxy information. And I suspect that that's the route that people will go. I don't know if anyone's thinking of doing that for cycle 2, but it seems to me an obvious plum to grab off the tree.
Marcia, this was fantastic. I have I guess it's a policy question. There must be some limit to the number of ultra disruptive TOOs.
Yeah, I actually tried. I tried to find that. I know that for the medium disruptive ones, they've promised 8 times a year. I don't know. I could not find a hard number for the ultra disruptive, but you're right. They couldn't do that a lot of times because it takes a fair bit of person power to get them into the queue and so on. And I should say that for the ultra disruptive ones, you pay a 30-minute allocated time penalty, so to speak, for them as well. But I think, if you've got something great to do, what's 30 minutes?
So I apologize that this is a little bit of a pointed question and it's a little bit unfair to ask you. I try to not ask questions like this, but some of the members are still a little bit disappointed at the naming of this new space telescope. So I was wondering if you have heard any thoughts or considerations to make sure that everyone feels comfortable getting involved with this great telescope moving forward.
Yeah, this has been an ongoing, issue, and you notice that as a member of the mission team, I get asked this, but we've been under sort of strict orders from headquarters, literally, not to get involved in the debate. So I said, okay, people have to go ask headquarters, but me as an individual person, I always try to just use the JWST right now and not actually say the name, and maybe we can figure out a way to turn those letters into mean something else. Maybe we'll still get the name changed, but for whatever reason, NASA seems very set on not changing the name. And for me, the naming had another really bad aspect that most people don't realize. The name was changed to this in, I think it was late 2002, and the name was changed without asking our international partners, and I thought that was the first name travesty, aside from who it got named after. So that's about as much as I'll say, but I'm sympathetic. Let's put it that way.
There are no more questions on the blue jeans or the Slack, and I see no one else standing up. So let's do a final round of applause for Marcia.